So in this class, we are going to learn the use of partial fraction in integration. Partial, whenever we have a fraction in which the denominator is splitted up, okay, like we have x plus 1 times x squared plus 3. Right now, this is expressed as a single fraction. Now, you don't have any rule to integrate such fractions, okay, directly. So what you are going to do is you are going to split this term into its partial fraction. So in partial fraction, we have done few cases. Do you remember all of those cases?
I think so.
Now, okay, before doing this, let us consider one example. Partial fractions. I'm just going to revise the first case. That was, for example, if you have 2 upon x squared minus 1. Now the denominator can be split up as x plus 1 times x minus 1. And whenever we have two linear factors in the denominator, the partial fraction was in the form of a upon the first linear factor plus b upon the second linear factor. You remember this?
Yes.
So then you would have you would have made the denominators common, x plus 1 times x minus 1. Would have been multiplied by x minus 1 and b would have been multiplied by x plus 1. Then you would have compared the numerators on the left and on the right. So 2 is equals to a times x minus 1 plus b times x plus 1. Then you would have substituted x equals to 1, and on the left hand side you are going to get 2. This is going to be eliminated and this is equals to 2b. So b comes out to be 1. If you would have taken as x as equal to minus 1, then b would have been eliminated and this would be minus 2a. So a comes out to be minus 1. So at the end, you would say that the partial fraction is minus 1 upon x plus 1 plus 1 upon x minus 1, right?
Yes, sir.
So 2 upon x plus 1 times x minus 1 can be expressed as its partial fraction like this. But what if we are asked to integrate this? Integration of this with respect to x is same as saying integration of the partial fractions. Okay, so we don't know how to integrate this, but if we can convert this into partial fractions, we can easily integrate these fractions. Now, integration of minus 1 upon x plus 1. If I take minus sign common, that is going to be 1 upon x plus 1 dx. So can you recall what was the integration of such functions, such fractions? 1 upon x plus 1.
Um,
What is the differentiation of the denominator?
X.
The differentiation of the denominator is 1. Is
Yeah.
the differentiation of the denominator present in the numerator?
Yes.
So the integration is going to be ln of the
Yes.
denominator. Similarly, over here, x minus 1 differentiation is going to be 1. So integration of 1 upon x minus 1 is going to be ln of the denominator. Make sense? Plus c at the end. Now, if you want, you can rewrite this ln x minus 1 minus ln x plus 1 plus c. And if you recall the properties of the log, if the two logs having the same base are subtracted, they can be expressed as a single fraction like this, x minus 1 over x plus 1 plus c. So that is the integration of this function. So
Okay.
now do you understand the purpose of making partial fractions and the use of the partial fraction in integration?
Yeah.
Okay. So let's consider this example. Find integration of 3 minus x upon x plus 1 upon x squared plus 3. Now, the first thing you always notice is the fraction an improper fraction or a proper fraction. How do we do that? By looking at the degree of the numerator and the denominator. The degree of the numerator is 1, whereas the degree of the denominator is 3 because x squared times x would have been 3. So the degree of the numerator is less than the degree of the numerator. It's a proper fraction. If it's a proper fraction, then we are going to see which form of the fraction is it. We have a linear and a irreducible quadratic. If you can just recall partial fraction,
Yeah.
irreducible quadratic, the general form of 3 minus x over x plus 1 times x squared plus 3, this can be expressed as a upon the linear factor plus bx plus c upon the irreducible quadratic factor. X squared plus 3 is the irreducible quadratic factor, so therefore we are going to have bx plus c in the numerator. Now that was the form of the partial fraction. To find the values of a and b, we are going to repeat the same drill. So a times x squared plus 3 plus bx plus c times x plus 1. And this is equal to 3 minus x over x plus 1 times x squared plus 3. You can just compare the numerators because the denominators are already exactly the same. So you can say therefore 3 minus x is a times x squared plus 3 plus bx plus c times x plus 1. Now you are going to take the suitable values of x to find the values of a and b and c. So if you take x as,
-1.
let's take -1 first. So we know that by plugging -1, this factor is going to be 0, which is multiplied by bx plus c. So hence this entire thing is going to be 0. Then if you plug in -1 over here, 1 plus 3, 4. So the right hand side will have 4a equals to 4. 3 minus -1 is 4. So a comes out to be 1.
1.
Now you can take x as 0 as well. If you take x as 0, what do we get? If I plug in 0, this b is going to be eliminated. If I plug in 0 over here, this is going to be just 1. C times 1, c. So I'm going to get 3a plus c equals to 3. And I know the value of a, that is 1. So c comes out to be
3, 4.
c comes out to be 0. That was at x equals to 0. And once you know a and c, now for finding b, just a second. Yeah, for finding b, I can plug in any value. Okay, you can take the simplest value you want, that is 1. So 3 minus 1 is going to be 2. 1 square is 1 plus 3, 4. 4 times a, which is 1, is 4. b times 1, b. c is 0. So b times 1 plus 1, 2. So you're going to get -2 equals to 2b. Hence b is going to be -1. Once I have the values of a, b, and c, I can make the partial fractions. The partial fractions is going to be a upon x plus 1
And
plus
-x.
b x plus c is 0. b was -1, therefore minus x 1x upon x squared plus 3. Okay, that's the partial fraction. Now at the end, we were asked to integrate this fraction. So integration of this fraction is equal to the integration of its partial fractions. So I can integrate these and the integration is going to result in what? Okay, so I know that this is going to be ln of x plus 1, right? Any problem in this? The integration of 1 upon x plus 1 is going to be ln of x plus 1. Can I say that? Hello? Uh, your voice has gone. If you can just reconnect, no worries. You can join in through the laptop. Sometimes it does give you a problem, so you can sign. You can like sign out and sign in again. I'll wait for you.
Hi, sir. Can you hear me?
Yes, I can hear you now. Can you hear
Okay.
me? Yeah.
Yes, sir.
Okay. Let's resume. Okay, so I was saying that would you agree that integration of 1 upon x plus 1 is going to be ln of x plus 1?
Yes.
All right. Now, what about this? We have x in the numerator and x squared plus 3 in the denominator. If I look at the differentiation of the denominator, that is going to be
2x
2x. How can I make 2x in the numerator?
multiplied by 2.
Multiply by 2. So I'll have to divide by 2 outside the integral as well. So this is going to result in ln of x plus 1 minus 1 upon 2 ln of x squared plus 3 plus the constant of integration. Okay, that should be your final answer.
Okay.
Go over this question once more and let me know if you need any help. If you want me to repeat anything. So let's compare your answer with mine. 9 over x plus 2 times x minus 1 the whole thing square can be expressed as a upon x plus 2 plus b upon x minus 1 plus c upon x minus 1 the whole thing square. X plus 2 times x minus 1 times x minus 1 the whole thing square. A would be multiplied by x minus 1 the whole thing square. B is going to be multiplied by x plus 2 times x minus 1. And C is going to be multiplied by x plus 2. So if you just equated the numerators now, 9 equals to a times x minus 1 the whole thing square plus b times x plus 2 times x minus 1 c times x plus 2. Let's substitute x as x as 1 first. If you substitute x as 1, a is going to be cancelled out, b is going to be cancelled out. 9 equals to 3c and c comes out to 3, right?
Yes, sir.
Then if we take x as minus 2, minus 2 will cancel out b. We are going to have 9a and it will also cancel out c, so a comes out to be 1. Then you can take x as 0, so 9 equals to 0 minus 1 and square is going to be 1. 1 times a is 1 plus this is going to be minus 2b plus 2c, and c value was 3. So it's going to be 6, 1, 7. 9 minus 7 is 2. 2 equals to negative 2b. So b comes out to be minus 1. As the partial fraction is going to be
Hello, sir. So your voice stopped.
okay. So I was saying that integration of minus 1 upon x plus minus 1 plus 3 times x minus 1 to the power of minus 2. Now you can integrate them in one go. Integration of 1 upon x plus 2 is simply ln of x plus 2. Integration of 1 upon x minus 1 is going to be ln of x minus 1. And integration of 3 times x minus 1 to the power of negative 2 is going to be 3 power divided by the new power plus c. So the final answer is going to be ln of x plus 2 upon x minus 1 minus 3 upon x minus 1 plus c. Are you getting the same answer?
Yes, sir.
I have expressed the final answer as a single log over here. ठीक है?
Okay. Yeah, sir.
Okay. Do you need time to note anything down, or should I move on?
So you can move on. I got the same answer.
Okay, I'm going to go over this once more. You were given two different types of function, and the strategy that we are going to follow is integration by parts. What I expressed, what I explained right now was integration by parts formula is derived from the derivative of is derived from the differentiation of like the product rule of the differentiation. UV in differentiation of UV is UV prime plus VU prime. If you integrate all the sides, you are going to get the integration of derivative of UV is simply UV equals to integration of u dv by dx plus integration of v du by dx. If you rearrange this and make this the subject, you're going to get uv minus integral of v du. Okay, now if I need to apply by parts, one of the function needs to be called u and the other function needs to be called dv by dx. How do we decide which function is going to be called what? By this acronym. The acronym is spelled as LATE, L-A-T-E. L stand for the logarithmic functions. Now, this logarithmic function will also involve ln function. A stand for algebraic functions. T stand for trig functions. E stand for exponential function. And the first letter will have the first type of function is going to be given more preference for you. So if you have two functions log and algebraic, log function is going to be u. If you have algebraic and exponential function, algebraic function is going to be u. So right now we have a product of x and x times e to the power of 2x, where x is algebraic and e to the power of 2x is exponential function. X is going to be u, okay? Because a comes first, a comes before e. So you are going to take u as x. Automatically, the derivative of v is going to be e to the power of 2x. Now you differentiate u and you integrate v, because when you apply by parts you need u v du, okay? So differentiation of u with respect to x is du by dx is 1, so du equals to dx. If you integrate the derivative of v, you are going to get v, and e to the power of 2x is going to be e to the power of 2x upon 2. Once you are done with this, you just have to plug in the by parts formula. U was x, v was e to the power of 2x upon 2, minus integration of v, which is e to the power of 2x upon 2. Du needs to be replaced with dx right now. Okay, then I just took 1 upon 2 as common out. Integration of e to the power of 2x came out to be e to the power of 2x upon 2 plus c. So the final answer is x e to the power of 2x upon 2 minus e to the power of 2x upon 4 plus c. Anything that you want me to explain again?
No, sir, I understood this.
Okay. So you can also see this integration of ln x as a product of 1 times ln x. And you can consider 1 to be algebraic and ln x to be the log. So if you use late, I'm going to take u as ln x and the derivative as 1. You can differentiate u with respect to x, you are going to get 1 upon x, and if you integrate v dv by dx, you are going to get v as x. Do you agree with me so far?
Yes, sir.
Now, if I have to integrate 1 ln x using by parts, that's going to be uv minus integral of v du. u is ln x minus v uv. So v is x. So I'm going to write x over here. Integration of x du by dx is going to be 1 upon x times dx, that is dx upon x. This can be cancelled out. You are going to get x ln x minus integration of 1 dx. And what is the integration of 1?
X.
X plus c. Hence, this is the final answer. Okay.
Yes, sir.
So there are some functions that might need to use integration by parts more than once to integrate a function. So let's consider this example. Using late, which one is going to be u?
X squared.
Yes, u is going to be x square. So dv by dx is going to be sine x. If you differentiate u, you get 2x, and du is going to be 2x times dx. If you integrate v, you are going to get v as, what is the integration of sine x?
Minus cos X.
Very good, minus cos x. So this is the differentiation integration. So now if I apply the by parts, integration of x squared sine x dx is going to be uv minus integral of v du. U is x squared, v is minus cos x minus integral of v, that is minus cos x du, which is 2x dx. So simplifying this expression, I get minus cos x x square, or it's a good way to write minus x square times cos x. This negative and negative is going to be plus. You get integration of, actually you can take 2 common out as well. So you get x cos x dx. Now how do you integrate this x cos x? Again, it's a product of 2 different functions. So these are the type of question in which you are going to use by parts again. Are you getting my point?
Yes, sir.
Just to integrate this, I'll have to use the by parts again.
So
So
X will be U.
again, u is going to be x, dv by dx is going to be cos x. You differentiate u, du is going to be equal to dx, and v is going to be equal to integration of cos x is sin x. So I'm going to take as it is everything, but for here, I'm going to apply by parts again. So uv x sin x minus integral of v, that is sin x, du is equal to dx. So I get minus x squared cos x plus 2 times x sin x. Integration of sin x is minus cos x, so this is going to be plus cos x over here because of the negative sign outside. This, and at the final, as a final step, I can add c. So my overall answer is going to be minus x squared cos x plus 2x sin x plus 2 cos x plus c. You get my point?
Yes, sir.
That's the final answer. So in these type of question, you might be asked to integrate twice. The by parts is going to be applied twice. Shall we move on to the next question?
Okay.
Given that integration of ln x upon x dx, use integration by parts to show that I is equals to 1 upon 2 ln x square plus c. So again, I'll have to use integration by parts. The function given to me is 1 upon x times ln x. So u is going to be ln x, and derivative of v can be taken as 1 upon x. If I find the derivative of u, I'm going to get 1 upon x. So du comes out to be 1 upon x dx. If I integrate v, I'm going to get, what is the integration of 1 upon x?
ln x.
ln x, very good. Again, now if I apply the product by parts uv minus integral of v du, u is ln x, v is also ln x. So this makes it ln x the whole thing square minus integration of v, that is ln x, times du. Now du was dx upon x. So this gives us ln x the whole thing square minus integration of ln x upon x dx, right?
Yes, sir.
Are you with me so far?
Yes.
Okay. Now you see the starting of the question. In what were we integrating at first? We were integrating ln x upon x, and then we came up to the same integral after applying the by part one time, that is integration of ln x upon x. Now would you agree that if I go for integration of this, I'm going to get this again and again and again? It's a never ending process, because integration of ln x upon x is going to be the same. Now if I integrate this, it's just going to extend my integration, but it's not going to end. Can you observe that?
Yes, sir.
So there's a smart way to tackle these type of question where the integration comes back to what the question was. So I started off by integrating ln x upon x dx, and I ended up with having an integration of the same function again. So what I'm going to do is I'm going to call integration of ln x upon x dx as I. Okay. If I take this as I, I'm going to get ln x square minus I. Are you with me so far?
Yes, sir.
If I just solve this algebraically, this minus I going on that side is going to give you 2I equals to ln x the whole thing square. And I is going to be equal to ln x the whole thing square upon 2, right?
Yes.
And we can't forget plus c, because every time there is going to be a constant of integration present. This is what we were asked to show. Okay,
Yes, sir. I'm just copying this down.
sure.